and kick it off. So welcome everybody for the Fluid Seminar, the Imperial Math Department. So it's a pleasure to have Carlo Camporeale today. He's a professor at Politecnico in Torino, and he's an expert in ripple formation in riverbeds and ice sheets, pattern formation in fluid systems, and in general morphological instabilities. And that's the topic for today: morphological patterns in glacial, karst, and alluvial environments, a hydrodynamic stability approach. So welcome, Carlo. The floor is yours.
Thank you, Peter. I'm delighted to be here. Thank you very much for the invitation. Let's start. And the focus my talk is, as already said, morphological patterns, but it sounds a bit far from the usual topics in fluid dynamics. But the point is that a key role is hydrodynamic instability in the pattern formation. A key point of my presentation, my talk, will be that the free surface, the presence of free surface and open channel flows plays a key role in the pattern formation and in the triggering instability. So I mentioned in the title 3 environments: glacial, karst, and alluvial environments. So let's do a quick review of an overview of why one should study ice dynamics. Apart from aesthetic reasons, we know that there are some important scientific reasons. Ice in ancient times covered 30% of the land area of the Earth. There are some issues related to structural geology and interest about paleoclimatology, the paleoclimatic reconstruction of the past climate, interaction with population in northern mountain lands. There is some interest, but some concern about proglacial lakes, which can produce dam break, so there is a risk of flooding. We know that 60% of the world fresh waters come from ice, so there is an economically valuable deposit, and everybody knows the problem about global warming and the hazard. And in fact, most of glacier and ice sheet in the world are melting. This calls for a new discipline which is called hydroglaciology. Interaction between glaciology and liquid water, which has some open issues, how the subglacial drainage network is organized, what are the dynamics of the inglacial or superglacial or subglacial channels. And this is important from the hydrology of the glacier during the melting of the glacier itself. For example, on the right, we see on the top the beginning of the formation of a supraglacial stream, which formed during the melting season. And because the glacier is a dynamic thing, there is the flow of the glacier englobe the channel sinks in the glacier, and the structure and the imprint of the surface superficial superglacial streams provide the imprint of the internal network of the glacier. It is fundamental to understand the hydrology and the way the glacier is melting. Why study caves instead? Again, apart from the spectacular environments they are, we know that karst covers from 10 to 20% of the Earth's land ice-free area, and about 25% of the world population drink water from karst aquifers. Again, paleoclimatic interests, and also karst environments are the last frontiers of the Earth exploration. But the main question is how did I come to karst and glacial environments? My background is basically fluvial morphodynamics. I did a PhD on hydraulic engineering, so I was very interested to patterns in fluvial environments, from ripples, bars, dunes to meanders, which exhibit a very wide range of length scales and landforms. So why study river morphodynamics? Rivers are highly dynamic systems, so for that they are very interesting. They interact with the landscape and infrastructure, drain nearly 75% of the Earth's land surface. There are some concerns and interest about hydraulic protection, so bridge stability, navigation, flow capacity, flooding, overbank flows. And also I want to mention as a last point that rivers today are well known that contribute very nicely to the global carbon cycle. So they are just not passive pipes, but provide a metabolism in the carbon cycle. So let's take a view to some pattern in supraglacial and ice morphodynamics, with increasing length scale from corrugation on icicles to what I call ice ripples on glacier. This is my photograph which I took on Chardonnay Glacier in Aosta Valley. This is not snow, this is ice. Strip-like patterns, channelization of bedières. Bedière is the French name for supraglacial streams. Also meandering of bedières, very large bedières in Greenland, kinematic surface waves of ice sheets, defect propagation, and so on. So a lot of patterns in ice morphodynamics. And there are also interesting similarities between alluvial and glacial patterns in meandering, ice and alluvial, and ripples on glacier and on beneath the water, on the bedrock of rivers, channelization on glacier, channelization on alluvial system. And this is one of the most important point of my talk, this kind of similarities. We have also pattern in karst morphodynamics, crenulation on stalactites, which are corrugations on stalactites, crenulation on stalagmites, patterns on flow stones, and scallops in close conducts inside the cave. So we have also similarities between glacial and karst patterns. You see crenulation and corrugations both on ice and stalactites, and also scallops, very similar indeed, both in caves and inside glaciers. So we have different environments, but very similar processes. Why? Because they share the same hand, the same reason of the patterning. That is hydrodynamics, in particular open channel hydrodynamics, the presence of a free surface. So the hand is hydrodynamics, the tool are different, sediment mechanics in alluvial system, in geochemistry, in karst morphodynamics, thermodynamics, in ice, or in glaciology, or in ice morphodynamics. So from a mathematical point of view, we need some governing equations. As usual, we have to consider mass conservation for the liquid phase, the continuity equation, momentum conservation with different strategies, 1D, two-dimensional, quasi-three-dimensional, and so on, heat conservation in the liquid and solid phase, in the case of hydroglaciology, and mass conservation of solutes and or sediments, in the case of karst morphodynamics. And then we also need, this is an important point, interface equation or evolution equation of the interface. In the case of alluvial morphodynamics, we have the Exner equation, which is mass conservation of the solid granular phase at interface between water and the sediment. The Stefan equation, that is just heat conservation at phase change interface. And PWP from Plummer, Wigley, and Parkhurst, I will come back later on that, but it's a sort of mass conservation, the solid solution interface. So as usually, we also need boundary conditions, and this is very important because we have a free surface, so a kinematic and a dynamic condition on the wall, and at the free surface, and some closure relationship, turbulent closure in the case of a turbulent problem, for example, in rivers, sediment transfer formulation, reaction kinetics coefficient, friction factor, and so on. And then strategies of solution. The most important step is to assume a quasi-steady approximation. That means that bed evolution dynamics are usually very slower than hydrodynamics. And then we can approach a problem through a 1D modeling that is done usually for sediment long waves or ice sheet flows. The shallow water approximation, so depth averaging, that is done for the study of bars, meander, also in the case of channelization of alluvial and so on. But remember that with shallow water approximation, if you study meanders, you always need something which resolve the three-dimensional secondary currents. If you neglect span Y variation, you can study subaqueous dunes, icicles, crenulations. If you neglect the span Y variation and the free surface, you just can study subaqueous ripples. Lubrification theory, it's fine for Parthenos pelotons and so on. I assume that everybody is quite confident with classical theory of stability analysis, maybe more than me. So I will go very quickly on this part. Main step usually are starting from the covariant equation, make a linearization of the equation, assuming a small perturbation to a basic state. So you're assuming a small parameter epsilon, and you're assuming a normal mode ansatz, so a particular structure of the solution, where omega r plus omega I is particularly important because it's the eigenvalue of an eigenvalue problem. And we have also the eigenvectors, which is the solution of the eigenvalue problem. And we know very well that the system is asymptotically stable if all eigenvalues have a negative real part. So it's enough to know the maximum value of the real part of the eigenvalues. And we also know that the celerity of perturbation in the, for example, in the longitudinal direction is related to with this kind of ansatz is related to the imaginary part of the eigenvalue. This is a very well-established theory. There is also a non-normal or non-modal theory. For example, Peter Schmidt is one of the most expert about that. We know that if eigenvectors, the eigenvectors system does not form a set of orthonormal vectors, it is likely, it's very usual to observe a transient growth, even though all modes are asymptotically stable. For example, in this picture, we have an asymptotically stable solution, but a transient growth. We have time, and we have here the so-called growth function. The growth function is something related to the energy of the perturbation. The formal definition is here. So we have a non-normal or non-modal analysis. We switch from an eigenvalue problem to an initial value problem. An example of application of this kind of tools is about we did about one-dimensional river morphodynamics. So take into account the Saint Venant equations, which are shallow water equation in a one-dimensional approach for shallow waters, so for rivers, coupled with continuity and coupled with the Exner equation, which is the evolution equation of the interface between the sediment and the water. So the displacement of the the bed. So we know that just the Saint Venant problem, so not considering the bed evolution, so the classical problem is normal. So the growth function is monotonically decreasing. So there is no transient growth. Instead, if we consider the mobile bed, so we couple also the Exner equation, we have a non-normal behavior, so a transient growth. And let me resume just the main results in river morphodynamics. One of the most studied problem in river morphodynamics is the study of bars. Bars are landforms, mesoscopy or megascale landforms inside the river channel, in the channel, which forms during flood events. So they are these alternate landforms which are alternating between left and right bank. They can be studied very well through a shallow water approach. So shallow water equation, but two-dimensional shallow water equation. So this slide is a sort of generalization to 2D of the previous one. Again, coupled with continuity equation and the Exner equation, plus of course reclosure relationship. And we know very well and very well established theoretical results, which are from the beginning the study of an instability, the linear instability. We know that when the aspect ratio is higher than a critical value, the aspect ratio of the river, we have the instability. It was also studied the convective absolute nature of the stability, weakling of the analysis. Floquet analysis was made by Philip Hall, a member of your department. Non-parallel effects, non-normality, and transient behavior. But it is all very well established now, but I want to focus your attention now to a sort of progress in this direction. This case here I show two rivers which have very similar hydromorphological conditions, very similar mean discharge, very the same granulometry in the sediment, the same slope, very similar width. But one is vegetated, the other one is not vegetated. Very similar climates as well. So there is an open issue in the community of people working on rivers. Why one is vegetated and the other one not? And our answer was that it depends on the hydrology, in particular on the periodicity of the discharges, in particular on the coefficient of variation of the discharges. We faced the problem through a stability analysis approach again, and starting again from shallow water equations. Again, you see the aspect ratio defined as the half wave over depth. And this is a classical result, what I already told, the instability inside the neutral stability curve at a value of the aspect ratio higher than beta critical. And going on, one can study also the weakly nonlinear analysis to arrive at the saturation of the amplitude of the perturbation of the bed through the center manifold projection approach, which is a bit different but very robust tool to derive the Stewart-Landau equation, very different from the classical one, which is focused on multiple scaling analysis. Anyway, this is the starting point. We adjoined an equation for the vegetation evolution that is basically a logistic growth. It's composed by the logistic growth with a carrying capacity plus a depth term. So we did a sort of secondary stability analysis starting from a new basic state, which is the basic state with alternate bars morphology already established, plus a periodic flow, plus the evolution of vegetation. We know that the use of periodic forcing calls for a Floquet theory, which provide, in this case, just one Floquet exponent. And when a Floquet exponent is larger than 0, in this case, vegetation develops. So this plan view, we see the morphology coming from the linear stability analysis of in brown is the morphology, and in green is the region where there is vegetation development. So where the Floquet exponent is larger than 0. And all this depends on, as I already said at the beginning, depends on the coefficient of variation of the periodicity of the discharges. And you see that if I define an areal vegetated index as vegetated area over the emerged area at low flow conditions, we see that this index depends on the coefficient of variation of the discharges, and there is a value, a threshold beyond which there is no vegetation development. And this is very well confirmed by comparison with satellite data. So this was done in a publication, PNS, some years ago. Let's move to meanders, another topic. Meanders is a bit more complicated issue because they develop bands, so it's better to use a curvilinear coordinate system. So we start from Reynolds average equations in curvilinear coordinates, and then coupling with the Vrinko decomposition for the secondary currents, which comes from a three-dimensional approach. And then after depth averaging, plus, this is important, the evolution equation in this case is this kind of integro-differential equation, which describe the evolution of the position of the center line depending on V. What is V? V is the bank retreat rate, the velocity of bank retreat, which is closed through this simple relationship, which is related V to the velocity in the water, very close to the bank. So the velocity at the bank. So through a constant, which is the erodibility of the bank, of course. So putting all together, people have resolved the linear stability analysis also in this case, and the linear problem, and so people now is able to make this kind of numerical simulations for the evolution, for the short-term and long-term evolution of meandering rivers. For example, investigating the selection of the lambda, where lambda is the mean wavelength of the meanders, of the curvilinear wavelength, of course. And also investigating the role of the particular role of oxbow lakes formation, the cutoff, which are this kind of abandoned lakes throughout the floodplain. So, what have we learned from river system? River morphodynamics is today a mature science, linear stability analysis, weakly nonlinear normality, absolute combinative nature, and so Floquet theory. So it's time to move to other complex morphological instabilities, such as those one. So karst and ice morphodynamics, using the same tools, so a unified approach, a unified methodology. Let's consider firstly the problem related to icicles or and ice ripple formation. On the left, we have this kind of corrugation on stalactites, which were investigated firstly by Ueno in 2012 at very low Reynolds number. On the right, a very similar problem, but which developed at higher Reynolds number on the surface of glaciers. I repeat, this is ice, is not snow. You see transversal perturbation orthogonal to the slope of the glacier. So they are shaped and formed during melting, during the formation of a thin flow of water, melting water. And the mathematical framework is under, of course, hypothesis of laminar incompressible flow, quasi-steady approximation, gravity field, starting from Navier-Stokes equations and adding heat equation for the liquid phase and for the solid phase. You see diffusion advection equation under the quasi-steady approximation. That means that we don't have any more time-dependent term in this equation, but just in the evolution equation, that is the Stefan equation, which calls from the difference between the gradient, the temperature gradient at the interface, the freezing melting interface between the solid and the liquid. Also, boundary condition at the free surface, we see dynamic conditions and kinematic condition, again, under the quasi-steady approximation. And also at the bottom of the ice, we can set both Neumann on Dirichlet condition. This is irrelevant to the stability. These are just technicalities, transformations, rectangularization of the domain, linearization. And at the first order, the zero order in epsilon, we get, of course, Poisson distribution for velocity, hydrostatic distribution for pressure, conductivity distribution for temperature in both the solid and liquid. At the first order, no surprise, we obtained the Orr-Sommerfeld equation, but a bit different from the classical and the standard Orr-Sommerfeld problem, because the boundary conditions are different because of course, the presence of the free surface. This was problem investigated by eminent people, or Sommerfeld, Heisenberg, Tolmien, Lin, Rader, Orszag. We know today that we have a long wave approximated solution for a wave number very, very small. Also, I did a series expansion solution for either Reynolds number, but I think my opinion is that the most accurate way to obtain the solution is through spectral methods. In particular, I use the Galerkin approach. Everything I know about spectral methods come from Claudio Canuto in Politecnico Torino, to whom I owe so much about teaching about spectral methods. And in fact, we applied spectral methods firstly in 2012, not for this kind of problem, but for another problem which I will show you later concerning Dune formation. Anyway, from this, we are able to get two important information from outer hydrodynamics, which is the vertical velocity and the displacement of the free surface. So, following a very similar approach, resolved what comes from heat conservation, so a forced parabolic cylinder equation, and also in the solid phase. In the solid phase is easier. We have the analytical solution. And we need, again, I repeat, the gradient, the difference in the temperature gradient at the interface. And all this is put in the Stefan equation, the evolution equation, that provide a dispersion relationship. So the growth factor, the eigenvalue, the only eigenvalue of the problem. And so the results are displaying the natural stability curve for different value of theta, that is the slope of the glacier. In the plot, we have alpha, the longitudinal wave number, and the Reynolds number. So the Reynolds number is an important parameter also for this kind of instability, that is a morphological instability. We see that is always a critical value of the Reynolds number for the morphological instability, which we can plot in this plot versus again the slope. But it's very different from hydrodynamic-like instability, the one from Benjamin Hill, which is the stability of the free surface, so the formation of roll waves in laminar condition. I forgot to say that all these problems display a phase velocity that is negative. So the morphological mode, the instability at the interface propagate upstream, both in the case of icicles and ice ripples. And also in this case, in the case of crenulation formation of stalactites, where the open questions when I faced the problem for the first time in 2012 was, what is the mechanism of formation, why the wavelength is roughly constant to roughly 1 centimeter, and if there is potential for paleo reconstruction from these patterns. The approach is very similar, but here we have in the realm of geochemistry, so we have to manage a ternary system, CO2, water, and calcium carbonates, calcite. Very basically, when water comes in the cave, there is a strong degassing of CO2, and so the water becomes suddenly very supersaturated in carbonates, and so tends to deposit calcite on surfaces. And this is the formation, the reason for this formation of stalactites and stalagmites. But there is the water. We have a thin film dripping on these surfaces. So we have to consider that, firstly, the reaction inside the water. We have fast reactions, slow reactions. I don't want to go in depth in these aspects. Anyway, from fast reaction, we can eliminate some species, and also considering the reaction at the precipitation dissolution interface, Plummer, Wigley, and Parkhurst obtained this kind of evolution equation for the bedrock, for the interface between the bedrock and the water, which is proportional to the rate of deposition of calcite, and also combining with electron neutrality condition, calcite solubility product, water ionic product. At the end, we know that the only unknowns are two in the system, the calcium concentration and the CO2 concentration. So, using the same framework as before, indeed it's a very similar slide, this one, but I have marked in green the differences with respect to before. Again, we have the same hypothesis, the same equation for the fluids, of course, again, Navier-Stokes equation. Instead of heat equation, we have a mass conservation equation for the species 2 mass conservation equation for calcium and CO2, but again are very similar, are diffusion advection equations and the quasi-steady approximation. Again, the same condition, the free surface, different condition for boundary conditions for C1 and the C2, and of course a different interface equation, evolution equation of the interface, but in this case is the PWP. But the approach And the mathematics is very similar, again, the same techniques, and of course, again, the all-summer problem, so this part is very the same. And we have to resolve two and not one parabolic cylinder equation, but with the same approach, put everything inside the PWP equation. This provides a new dispersion relationship. In this case, is quite cumbersome, but is algebraic as well. And we are able to, of course, display the distribution in the concentration of the species inside water, which drives fluxes on the interface. Anyway, the most important thing is to obtain the selected wave number. Alpha m is the wave number, so the reciprocal of the wavelength, that is selected from the instability versus the Reynolds number, or this angle beta. Beta is this one, you see, is related to the celerity of propagation. In fact, you see the arrow is the flow, is the direction of the flow, which generated the stalactites and also the perturbations. And we see the celerity, the propagation of the maximum. So beta is related to the celerity of propagation, and it is very well dependent on Reynolds number. So this is an opportunity for a new proxy for cave paleo flow reconstruction, because from just cutting a stalactite, see what is the geometry and recorded in the rock, and from that, through the theory, reconstruct the Reynolds number, that means the magnitude of the flow which generated the pattern. We have some related problems to this one. For example, the study of draperies and flutings. In this case, again, we have the positional patterns, but or sometimes dissolutional. Instead, in this case, sorry, is dissolutional patterns is due to undersaturated condition. But the point is that we are at inverted conditions. I mean, overhang, the water is beneath. And so there is a sort of competition between gravity and surface tensions. Of course, this is, again, a standard problem is the Rayleigh-Taylor instability, but in this case we are focused on the presence of a stream, the presence of a current, and of course we are focused on the morphological instability. You see that in condition we see these things which are organ pipe shaped patterns, which develop in the inverted part. Instead, in the normal part here of the dome, there is not the channelization, but something else. You see channelization here and not here. You can see also this on old fontaines. So using a very similar approach, at the end I get this kind of plot. Here I plotted the growth factor in terms of the longitudinal wave number and the transversal wave number. So you see that we have both on the alpha and also on the beta axis, but the most important one is on the beta axis. And maybe I have a problem with the connection. Me?
Yeah,
Peter?
you're breaking up a little bit, but it's still okay, I think.
Okay.
Carlo? Yeah, there seems to be a little bit.
Let me.
Sure.
I can my. Okay, maybe.
Carlo, can you hear me? Oops, I think we just lost him. Oh. Carlo, I think you're muted.
Sorry, now I think my problem with connection is resolved.
Yeah, okay, you're back.
Sorry.
If you want to share the screen again and then keep going. Yeah. Perfect. Yes, very good.
Yes, I want just to.
Yes, we can see the slides now.
This one? Okay, I was here.
Yeah, you were here. Yeah.
Okay.
Mm-hmm.
Yes, I just saying that from the stability analysis of this problem, and you see approach this lateral with radius of curvature of the dome. So I studied this part, the overhang part, and the plot of growth factor in terms of alpha and beta. And you see that the most important instability in the overhang part is on the beta axis. Beta is related to the transversal, to the channelization, so the transversal wave number. And again, here there is for paleo flow reaction, because in this plot you see the radius of curvature, the slope of the inverted part, and the Reynolds number, and so we can the Reynolds number, of course, which generates the most unstable pattern. This is a recent paper, which is a sort of a progress on the same line, but this is more related to linear current, which are dissolutional patterns which form not at inverted condition, but in normal condition. So they are erosional pattern, but erosion comes from dissolutions because the flow is undersaturated. You see that there is an increasing of the concentration in the carbonates downstream. So there is also a dependence on X, the long stream coordinate. Again, the same approach, I don't repeat the methodology, the same approach provides the solution. So we are able to which are very small patterns, real and current, one current, in terms of Reynolds number. So again, Reynolds number, so hydrodynamics is a particular important parameter. So come back to river morphodynamics. Standard problem in this case is the dune formation, which are short wavelength patterns, so they are shorter than bars, and they are strictly related to the hydraulics, the hydrodynamic of the wall column, and also the interaction with the free surface. So they are not long waves, but short waves because they scale with the depth. So we need an approach which takes into account the hydrodynamics of the wall column, so not a shallow water approach. So again, the same approach. The same framework, but using turbulent incompressible flow, sediment transport should be considered now. Of course, we have to manage Reynolds equations because we are in turbulent conditions, so Reynolds stress through a turbulent closure relationship. For example, algebraic model, mixed length theory. At the free surface, we have again dynamic condition, but without the role of the Weber number. I didn't mention it before, but in the previous case, we had a Weber number, that means surface tension. In this case, turbulent flow doesn't need to consider also to surface tension. And of course, at the siltation layer, we have again Exner equation in place of, for example, Stefan or PWP equation. But the approach is the same, different solution for the basic state, the log law for turbulent flow, and at the first order, we have not strictly an Orson method equation, but an Orson method-like equation. But again, we are able to get vertical velocity and displacement. This was the problem which I firstly managed with a Galerkin approach with the aid of Professor Canuto. And from that, we are able to reconstruct this well-established plot where the growth factor is plot in terms of Froude number, and maybe Englishmen say Froude number. Italian people say Froude number, but I think it's better to say Froude because Froude was Englishman. And the longitudinal wave number, you see Dune instability, that means pattern propagating downstream, anti-dunes instability pattern propagating upstream, and also the formation of roll waves. In this case, we kept the time derivative in the kinematic equation, if I remember well, and this was enough to see the roll waves formation. So also a sort of hydrodynamic instability, altogether with the morphological mode. So, just concluding, water-driven patterns are widespread in geosciences. And then a morphodynamic approach using fluid dynamics, combining fluid dynamics and interface equation is a powerful tool for investigations. Free surface dynamics appear a key element, and there is some potential for paleo flow reconstruction in the case of karst morphodynamics. That's all. Thank you very much.
All right, thank you very much, Carlo. We're going to open the floor for questions. If there is some questions from the audience, please raise the hand or just unmute yourself. That's probably the easiest. So let me kick it off with a question. When you see all these instabilities, especially the ripple instabilities, there also seems to be a transverse instability in the transverse direction. So is this a true secondary instability on top of the primary instability, or is this more a consequence of a changing base flow? Can you distinguish the two instabilities?
Is a transfer instability, you mean the transfer, two-dimensional instability, not just transversal but longitudinal, combining all together?
Well, there is first the primary, the ripple formation, and then there is a secondary instability in the transverse direction. So my question is this a true secondary instability, or is this based on a evolving base flow that is actually, still part of the primary instability?
No, I think that is basically, again, a primary instability, but two-dimensional. If you do linear stability analysis, not just in the alpha, but also in beta, you should see something that is not just on one axis, but somewhere combining alpha and beta, that are called, yes, at nonlinear level, they are rhomboid instabilities. Yeah. Linearly speaking, they are just a combination of two waveforms in X and Y. And yes, something like that. Of course, at the nonlinear level, we have something very, very much more complicated in 2D.
Yeah, yeah. All right, Shusong, you raised your hand. Please unmute yourself and fire away.
Okay. Yeah, very interesting talk. Thank you for sharing your work with us. Okay, I would like to ask the time scales involved. So you have these instabilities. Basically, you have growth rate. On what determines the time scale? Can you hear me, Peter, speaker? I can't see speaker now.
Carlo, I think at least your picture seems to be frozen. Uh-oh. We may have lost him. Oh, here he goes. He probably, let's give him a minute. He may reboot and come back in.
Yeah, he'll probably come in.
I was saying a while ago how good these online seminars are. Everyone can join. It has its downsides.
Yeah, that's okay. Seems to be a little bit of a bigger problem. Oh, connecting to audio, he's coming back.
I'm so sorry. I did the worst choice staying at my home today. Yeah. I think so. Sorry. So I didn't I didn't hear.
Did you hear the question? No, Shusong, you wanna formulate the question again?
Oh yeah, sure.
Yeah.
Okay, my question is about the time scale of the instability. The reason I'm asking is that the pattern we observe must be kind of saturated or developed patterns developed over a very long time scale. So I wonder what's the relation between the patterns you predicted by linear instability, usually based on a flat basic state. You know, how is that going to be preserved for very long time?
Yeah. Yes, yeah. We have to split to separate the question length scales and time scales. Of course, time scales is related to non-linear evolution of the
Evolution, yes, yeah.
So, of course, when you see finite amplitude of the instability,
yeah,
this is strictly related to non-linear issues. But I think that in most of the problems, the imprint of the linear stability that triggered the instability remains also at long times. Of course, we can also observe non-linear change in the wave number, but is another non-linear issue. But most of the time, then the linear instability has given the imprint of the pattern. So also at long times is on that imprint.
Mm-hmm. I mean, okay, so in some situations, for example, these dunes, once the pattern formed, they would affect the flows, right? So the interaction between the solid phase and the fluid would be different.
You mean there is an interaction between
yeah, the emerging pattern, the pattern actually deviates very significantly from a small amplitude assumption. Then
yeah, of course.
Yeah.
Yes, this is the question. Okay, if you do a weakly linear analysis, all this is taken into account. For example, I showed the amplitude saturation. This kind of amplitude saturations takes into account altogether also the feedback of
yeah, I know, but you can only do that near
the fluid.
Near critical conditions, right? Once the system evolves and it may deviate from critical conditions, then you can't do weakly nonlinear.
Yes, yes, I see what you say. The near critical conditions is a shortcoming, I think, of the multiple scale analysis. If you use if you use this one, the approach I used, let me see, just one moment. Can you see my screen? Not, I think.
Not yet.
Oh, sorry. Yes, the center manifold projection approach. I didn't remember the name. Sorry. The center manifold projection approach doesn't require to stay close to the critical condition. So you can stay also far from the critical condition with the center manifold projection. You have just to ensure that the perturbation is not so high, so it's not very small, but neither very high. Anyway, there is not a shortcoming of multiple scaling, so you can stay. Anyway, also with the multiple scaling, it is well shown that the selected wave number also at higher value with respect to the critical condition is usually quite the same with respect to the critical one. Mm-hmm. This is true, for example, in the bar instability.
Mm-hmm. Can I ask something, Carlo? I think now you can share the screen as well, by the way. I think it was the problem that was the ripples, the 2D ripple formation. I think maybe it was the ice problem. I can't remember. But you showed the figure where you showed the critical Reynolds number. The wave number, I believe.
Yes, let me see. Yes.
For various situations, right? There was lots of neutral curves. Yeah, a bit further down. That one.
This one.
Yeah, that one. I guess my question is that the the dashed curve, right? The dashed curve, which is lower, that's the surface mode instability, right? That's the free surface.
Yeah.
Now that's lower. So doesn't that mean that it would be more unstable than the morphological?
Yes, it's more.
And
yes, then, it's more unstable. Yes, I agree.
And then doesn't.
But it doesn't matter because stability analysis. So the two modes are quite independent. So they don't fight together.
Yeah, I agree with that. But the moment. The moment.
Actually, I have to. Sorry. In my framework, in the numerical, I resolve this problem both analytically and numerically, in terms of the flow field and so on. When I did that numerically, I relaxed a bit the quasi-steady approximation. So I saw all the modes, the morphological one, the hydrodynamic one, and the surface mode, all together. And yes, the surface modes appear at lower Reynolds number, so it's more unstable. But that means that at this value of theta, you have, for example, at higher Reynolds number, two unstable modes, of course, the morphological one and the surface one. I can show you maybe somewhere I have the paper, the spectrum of the modes.
Mm-hmm. But that when you treat all the modes together, you keep them at the same time scale, I guess, right?
They have different time scales, of course, yeah, because the hydrodynamic mode is very faster.
Yeah.
I can show here the spectrum should be. Oh no, sorry, that's another problem. Oh, sorry. Yeah. Let me see, just remember. Okay, this here you can see the spectrum. So omega r, omega I. You see all the modes. You see also solid induced thermodynamics modes. And in box C, that is this one. Can you see? The fluid-induced thermodynamic modes, this one, and also the hydrodynamics modes, this one. So it's all together.
Mm-hmm.
And let me see. There is no, morphological mode is here. It's there. And so let me see. Omega r is 0.002. Instead, you see that the axis is times 10 to 6. So there is a very different separation in the growth rate. That means different time scales, of course, because the time scales is the reciprocal of the growth rate. So it's completely different. Morphological one is completely different in the time scale.
Mm-hmm.
Yeah, but how can you can describe them by the same set of governing equations?
Yeah, because but it's not exactly the same that I showed you with the slide. This is without the quasi-steady approximation. So the equations are the standard Navier-Stokes equation with the derivative term. So in the let me see, in the Sommerfeld problem, I just matrix notation, so it's not so easy to understand. But there is the time derivative in the Sommerfeld equation, time derivative in the kinematic equation, also time derivative in the dynamic equation. So it's the full problem, which can be resolved just numerically.